next problem is called minimum depth of the binary tree. We are given a binary tree and we have to find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root to node down to the nearest leaf node. A leaf is a node with no children. So for example, this here, the node 7 doesn't have left or right child. So basically it represents a leaf node. The same goes for the element node 15 and the node 9. So because in this case, the shortest path from the root to the leaf is from 3 to 9, which only contains 2 nodes, we will just return 2. The number of nodes in the tree is in the range 0 to 10 to the 5th, and the values of nodes range from -1000 to 1000. Now, there are two algorithms that can be used for getting the minimum depth of binary tree. One is called BFS, and the other is called DFS. So the breadth first and depth first search. For the breadth first search, we already faced it when we were solving the problem average of levels in binary tree. We are traversing the binary tree by levels, basically. In this case, we will hit the shortest path in the second level, so we will not be covering the rest of the binary tree. And DFS is the better alternative in this case to calculate the minimum depth, because in the DFS we are basically traversing calling recursively the DFS function until we hit leftmost node that doesn't have any children. It's a leaf node. So we can have a depth of here like of 10,000, and then in our right subtree we can have only one node that's a leaf node, which represents our shortest path. So in that case, we would lose all of this time to calculate something that we don't really need. But if we choose to do it level by level, we would find it in the first level, because we would be checking the first element in the left subtree, but also the first element in the right subtree, which represents the nearest leaf node, together with the root that forms the shortest path. So the BFS will be the algorithm to use for this problem. Now, we first check if the root is equal to none. We have an empty binary tree, so we just return 0. That's the shortest. Basically, that's the depth, because depth 0, because there are no nodes inside the binary tree. Otherwise, we declare our queue that we'll be using to perform the BFS. We just add our root node to the queue, and we initialize the level to be level 1. Next, we basically, why are we declaring it this one? Because if we have only one node that's basically also the root node, and depth will be 1, not 0. So we will iterate over as long as we have elements in the queue. We will first get the size of the current of the queue, and then we will iterate as long as the size is larger than 0. Each time we are getting the node, we are pulling the node from the queue, and we are checking if the node is a leaf node. If it is, we just return the current level. But if it isn't, we have to check if the left and right node are defined, so we can have it for the next level. And we have to increment at the end of the iteration. We have to increment the level. Finally, we just returned the level that's basically the deepest level that we have, because we haven't returned early. For the time and space complexity, as in the average of levels in binary tree, because we have a queue, we have a space complexity proportional to the size of number of binary tree nodes, and because we are traversing through all of those nodes, we have also the same time complexity.